We're going to continue our discussion on differential equations by considering initial value problems. So let's first quickly review what we know from integration because I think it's going to help us a lot. So let's think about an example. So let's say we have some object, for example, a car, and let's say it's moving with a constant velocity. So it's constant velocity. And let's say we are going to denote a position function x of t. So this is going to be the position at time t. So we could just call it the position function. And then let's say we are going to say that x naught is the initial position. So that's the position when time is equal to 0. So let's write this a little bit more mathematically. So we know that in general, we know that the velocity function is equal to the derivative of the position function. So dx dt should equal the velocity function. Here, velocity is always constant, so it's just going to be a constant. And secondly, we know that x of 0, so when time is equal to 0, the position is x naught. That's what initial position refers to. So x of 0 is equal to x naught. So we have those two pieces of information. Now, let's try to think about how we solve for what x naught should be. Sorry, not x naught, what x of t should be, what the position function should be. So in order to do this, usually what you would probably think of, because we didn't talk about differential equations yet, is you'd want to integrate the velocity constant or the velocity function, because of course, if we integrate the derivative of a function, we're going to get that function, right? That's what the derivative does. It kind of undoes the derivative, you could think of it as. So this is also equal to, of course, the integral of v naught dt, because the v naught is equal to the derivative. And so here we're going to have x of t, and over here, well, v naught is just a constant, so simple integration would have that, and also we can't forget the plus c, because we don't, we're just going to put this aside for right now, we'll deal with this after, but if we didn't have this, right, we would have to have that c there. And so this is what we would call the general solution. That's the general solution. How do we find the specific solution? Well, we use the second piece of information we had. We know what x naught refers to, we know what x of 0 is. So let's plug in t equals 0 into our general solution. So x of 0, well, the first term goes to 0, so we're just left with c, and that is equal to x naught. And so that tells us, therefore, that x of t should equal v naught t plus x naught. And so this now becomes the particular solution, because we no longer have that arbitrary constant c. Hopefully that's very familiar to you, because that's what we do quite often with integration, and it's going to help us understand initial value problems a lot better. So let's go into what we actually mean now with initial value problems. So initial value problems are IVPs. Well, first I'm going to only consider first order ODEs. That's what I'm going to look at right now. So first order ordinary differential equations. Okay, so let's think about the general idea for what a first order ordinary differential equation would look like. So we would have y prime equal to some function of x and y. What does this mean? Well, you could just imagine we've isolated for the first derivative, right? Because we're looking at first order, so we only have the first derivative at most. Like we're not going to have like the double prime or anything like that. And then on the other side, we're only going to have some sort of combination of x's and y's. That's at most what we're going to have. So right now, this is not an IVP as it looks right now, because if we would try to solve whatever this function might be, right? We don't know what f is, right? We don't know what that is, so we can't solve this yet. But assuming we did know, even if we did solve it, we would, in general, we would have a general solution, of course. So what makes this an IVP, or initial value problem, is that we have an initial condition. So we would have somewhere that y of some x naught is equal to some y naught. And so this is what we call an initial condition. Effectively, you could think of as a point on the curve y of x, right? Because that's what we're trying to solve for. And so together, this makes up the IVP. Now let's just think about why this initial condition is quite important. So let's think about just if we had a normal axis here. And of course, we don't know the specifics of this equation, but let's just say I had something that looks like this maybe. And let's say that was the solution curve, right? So here's y and here's x. And let's say this is what y of x ends up being. Well, if I didn't have this initial condition, in general, I couldn't say that that is the answer, because I'd have like a family of solutions. I'd have a general solution. So I might have very similar looking solutions. But because I'm given this initial condition, I now can narrow it down because I can specify that a certain point is on it. So for example, let's say this is x naught, y naught. And because I know that's there, now I can narrow it down to a particular solution curve. So now that we know this general idea, let's think about when we can solve for a unique solution. So as I tend to do in these types of intro videos, we're just going to look at an overview, and then in the next few videos, we're actually going to look at different ways of solving these differential equations. So this is the question now. So when can we find a unique solution to what we were looking at before? So when can we find a unique solution to y prime equaling f of xy? And so when I say unique here, unique means we are looking for one solution, not multiple and not none. We want a unique solution. And when can we find that? Well, there's a theorem actually. And I'm not going to prove the theorem here. We're just going to take it for what it means and then apply it. So what is the theorem? Well, the theorem says that if f of xy, so we're talking about the same f of xy from up here, if f of xy and the partial derivative of f with respect to y, and of course that's of xy, so hopefully this doesn't look completely strange to you. The partial derivative here we have to consider because this function f has two variables, so it's going to be a partial derivative. So if those two functions are continuous at that initial condition, so at x naught, y naught, if they're continuous at that point, then the theorem tells us that there exists a unique solution for y of x. But a little subtlety here is that that's for x not equal to x naught. So like I said, I'm not going to go into the very details of how you get this theorem, but this last part here, which kind of might seem a little confusing, don't worry too much about it. It's really just for completeness, just to have the complete theorem that's with all the technicalities there. But really you could think of what this means is that in the vicinity of that point x naught, y naught, we would have a unique solution. But don't get too concerned about what that actually means. It's just there, again, just for completeness. So now let's try to apply this theorem before we finish the video in two examples. So we'll see how this theorem works. So let's think about some examples. Okay, so first, let's think about this IVP. So let's say that y prime is equal to xy, and also that y of some x naught is equal to y naught. And let's let that be our initial value problem for this example. So let's write down what we know. So if we're using that same form that we were thinking about before, f of xy should equal, or let me use the same notation, f of xy should equal xy, right? Because as we said up here, in general, we're going to say that y prime is equal to some function of x's and y's. So here we have the y prime is xy, so therefore f of xy should be xy. And secondly, for this theorem, we need to find the partial derivative of f with respect to y. And so what would that be? Well, the partial derivative of f with respect to y is in general going to be a function of x's and y's, but in this case, it just boils down to an x. Now let's think about these two functions. Well, we have xy and we have x. Well, there are no restrictions. These two functions are continuous for any input x and y, for like any of those as real numbers, right? These are always going to be continuous. So even though the theorem was specifically if it was continuous at x naught, y naught, here it is continuous there, but it's continuous everywhere. So therefore there is a unique solution. There is going to be a unique solution for, actually, what you might realize, it's for any initial condition, because we didn't actually specify what x naught and y naught are, right? We didn't even have to use it because it was always continuous. So for any initial condition, y of x naught is equal to y naught. So that was fairly simple. Now let's think about something a little bit more complicated. So let's say we have this IVP. So we have that y prime is now equal to the square root of y. And we're going to say that y of 0 is equal to 0. So the point 0, 0 is on our solution curve. So that's what we have. So again, let's write out what we're looking for. So first, what is f of xy? Well, here, we don't have any x's here, but that's not a problem, right? Because this is just, this f here is referring to, in general, what we would have there. In our case, though, we don't have any x's, so we just have the square root of y. Now, immediately, you should realize that this has a restriction. Y has to be greater than or equal to 0, which is okay for our case because so far, if we're just thinking about the function f, the theorem says that it has to be continuous at the point x naught and y naught. And that's okay because we have that y of 0, right? We have that x naught and y naught is the point 0, 0. In this function f, there are no x's to worry about. And for the y, it's okay because we are greater than or equal to 0. So we're okay so far. But we also have another function to think about. And that's the partial derivative of f with respect to y, which again is in general going to be a function of x's and y's. And so if you work that out, you're just taking basically the derivative of this because there's only one variable anyways. We get 1 over 2 square roots of y. And so this one is a bit more interesting because it's actually not continuous when y equals 0. This is not continuous because if y was equal to 0, we'd have the denominator equaling 0. So it's not continuous at y equals 0. So therefore, based on the theorem, there isn't going to be a unique solution. And in fact, we're going to see how to solve these later on anyway, so don't worry about this right now. But just to drive the point home, this IVP actually has 2 solutions. So this doesn't mean that it has none. It just means that you don't have you don't have just one single solution. And just to show you, the solutions here would be, we would have 2. So we'd have y1 of x could be 1/4 x squared, where x is going to be greater than 0. And we could also have a second one where it's just equal to 0.